So we now have direct from London, Matej Balog from Deepmind, who will tell us about FunSearch.
Thank you. Hello, everyone. In this talk, I'm going to tell you about a system called FunSearch, which is a system that is able to leverage large language models in order to make new discoveries in mathematics and computer science. My name is Matej Balog. I work as a research scientist in Google Deepmind in London within the science unit. And the work I am presenting here is on behalf of the whole FunSearch team. So just for the context of why we did this work and why it has happened at Google Deepmind, this is the mission of the company. We aim to build AI responsibly in order to benefit humanity. And an important part of the second part here, benefiting humanity, is showing that AI can meaningfully contribute to advancing the sciences. Now, of course, most famously, this has been done with AlphaFold in biology by solving the protein folding problem. But we are trying to replicate the same thing across different scientific disciplines, including chemistry, physics, mathematics, and now computer science itself. And that last part is what our specific subteam is aiming to do. In particular, the mission of our smaller team is to discover new knowledge and efficient algorithms for impactful problems using AI. Now, if in case you have followed our work maybe 2 years ago, previously we built a system called Alpha Tensor, which was again an ML-based system, but based on reinforcement learning that was able to discover new algorithms specifically for the problem of multiplying matrices. But in the work that I will be talking about today in FunSearch, we have been aiming to be much more general and also use a very different class of techniques, namely see whether we can utilize large language models for the discovery of new knowledge or new algorithms. So I think it's quite likely that many of us have tried using a large language model to solve a very difficult problem, maybe so difficult that it's an actual open scientific problem. And I assume that in all those cases, the outcome was not that the LLM responded with the solution and thereby solving the open problem, but instead maybe came up with some hallucination or at best like a vaguely plausible set of ideas how one might go about solving the problem. And so how can we address this shortcoming of LLMs, let's say often hallucinating? So the central tenet behind FunSearch is this idea that we are going to ask the language models not to give us the responses in natural language, but instead we'll ask the language models to provide their answers in the form of computer source code. And this has one key advantage, which is that the responses we get from the language models, we can actually execute them by running them on a computer. And by observing the result, we can actually tell automatically which of the responses were good and which of them were bad. And thereby, we can ask the language models many times and identify the occasional gems where they actually come up with some useful idea that performs well. And then we will be able to couple this idea with evolutionary algorithms that will be able to iteratively develop the better and better ideas into something that's really good. So another possible view of what we are trying to do here with FunSearch is that we are building towards this vision of P equals NP in practice, which means that we are looking at problems which have the following property. They admit a fast evaluator in the sense that if there is a candidate solution to the problem, it's fairly easy to evaluate how good that solution is. But solving the problem in the first place is very hard. And you'll be familiar with the computation, with the class of problems, NP-hard problems, NP-hard optimization problems, which exactly have this feature that they're difficult to solve but easy to evaluate. And so you can see FunSearch as kind of a box in the middle that, given an evaluation function, will produce a function that solves the problem in practice. Another viewpoint is that FunSearch is going to combine two different components that very nicely complement each other. One is the creative power of large language models that are able to come up with a diverse set of ideas, potential solutions, admittedly many of which might be not very useful, but this will be coupled with an exact evaluator that is going to identify the occasional gems and extract them, and then we can iteratively build upon them using evolution. So as a first use case or case study that we applied our ideas to is the capset problem. So this is a key problem from extremal combinatorics. At some point, Terry Tao on his blog post mentioned this might be his perhaps favorite open question. Now, this was admittedly before the asymptotic conjecture was settled, but still. So what is this problem about? In the capset problem, we want to construct large sets of points in the space Z3 to the D, so D-dimensional space in arithmetic modulo 3, such that no 3 points are collinear or lie on the same line. So just for intuition, in one dimension, there are 3 points, and the best you can do is to include 2 of them to form a set that does not have 3 collinear points. Such a set is called a capset. And so in one dimension, we would say the size of the largest capset is 2. In 2 dimensions, the situation is still fairly simple. And it's maybe not obvious, but one can easily check manually that you can include 4 points without any 3 being on the same line, but it's not possible to have 5. As a random example, if you were to include this point in the upper right corner, then you would have 3 points on the same line on the diagonal. So here we would say the largest capset in 2 dimensions has 4 points. You might start to think the size of the largest capset will just be 2 to the dimension, but that already breaks down in 3 dimensions, where it turns out that you can have a capset of size 9 as opposed to 8. And in fact, the size of the largest capset is known up to 6 dimensions. But beyond that, it is an open question. What is the size of the biggest capset in any specific number of dimensions? And it's also an open question, what is the asymptotic rate of growth of the largest capset as the dimension grows? So why is this a good problem to look at with FunSearch? Well, it has some nice properties. One is that if we come up with a candidate solution, it's very easy to verify its correctness automatically. And given a candidate set of points, we can easily check whether it's a capset by checking all triples of points, whether they lie on the same line or not. And it's also easy to measure how good a candidate solution is. The goodness just corresponds to the size of the capset. So what this means, we can write an efficient evaluate function. So how can we use a large language model to help us with this problem, in particular in a way where it responds with computer code? So, and in case you're not familiar with Python by any chance, I'll just describe this in words. So first, we have a function called build capset that is going to build a capset in a particular way. It's going to include all the elements from the high dimensional grid that satisfy some predicate, which is called isInSet, and that will be defined later. And then to evaluate a candidate solution, what we are going to do is we are going to call this build capset function. This gives us a set of points, and then we'll check whether they actually form a capset, and if so, how big that capset is. That will be the measure of goodness. And so the critical piece is defining this isInSet predicate, which will decide which points to actually include in the capset. So one candidate that actually works in 2 dimensions is this one, like some random Boolean predicate. And then what we can do is we can form a prompt for a large language model, which will have this format. Like it's basically what I was showing before, but the starting function isInSet. We rename it to isInSet _ v0, indicating that this is kind of a starting function or maybe a silly function that doesn't perform very well. And then below that, we include just the header of kind of an improved function. We can call it isInSet _ v1. We include a doc string saying that this is a better version of isInSet v0. And then we end the prompt there, leaving it up to the large language model to complete the body of this function. ideally producing something that's better. So let's say maybe in this case, the LLM slightly modifies the predicate by changing the equality to inequality. And indeed, if we were to run this in 2 dimensions, this would constitute an improvement because the original function only gives a cap set of size 2, and this one would give us a cap set of size 4. And so if we are in this situation where we got a better function, we can move that improved function into V0 and then show this prompt again to the language model, this time asking it to improve upon the already improved function. And of course, we can do this iteratively whenever we have an improvement. So just as an intuition why this can work well, let's say this is the starting function that we can provide, some easy function that constructs cap sets which are valid but very small. And so we are in this region of the space of functions. Here blue means low scoring functions, small cap sets. And let's say we want to get to this region like dark red where we have the high scoring big cap sets. Now it's very unlikely that if we ask an LLM to just improve the original function, it will straight away jump to the high scoring region. But it will likely generate some candidates in the immediate neighborhood of the starting function. And because we have the exact evaluator, we can identify those candidates that kind of are moving in the right direction. And then we can iteratively build on top of that, on top of those, and gradually move into the region of the space that has the high scoring functions, eventually being able to construct very large cap sets. So what kind of results are we able to obtain with this approach? So as I mentioned before, the size of the optimal or biggest cap set is already known up to 6 dimensions. And in all those cases, FunSearch has been able to find constructions, meaning pieces of computer code that construct cap sets of those sizes, matching the best known. It also matches the best known in 7 dimensions, although that might not be optimal. And then excitingly, in 8 dimensions, FunSearch was able to find a cap set that was strictly bigger than what had been known in the literature by that point, demonstrating it's able to discover new knowledge. And then maybe even more excitingly, what we care about in this problem in particular, like even more than the size of the largest cap set in a specific number of dimensions, is the asymptotic rate of growth of cap sets as the dimension goes to infinity. And FunSearch has also discovered a finite construction that I'll talk about later, which improves this asymptotic rate of growth. Now, even though numerically that improvement might seem very tiny, it is actually the biggest improvement in the last 20 years on this particular lower bound. Now, I talked about the numerical results, but what I think is also quite interesting is that usually you would think of a cap set when you apply computational search to this problem as this incomprehensible list of numbers. Like here on the slide, I'm showing these 512 vectors, each of length 8, that constitutes this newly discovered cap set of size 512 in 8 dimensions. And by looking at this grid of numbers, we probably cannot infer much beyond the fact that this set exists. But what's nice is that because we used FunSearch to look for a piece of computer code that builds this cap set, we also have this additional artifact, like a relatively short function written in Python that builds this cap set. And so this is, of course, much shorter. And as a result, as humans, we can start looking at this piece of code and derive some understanding of how to build the cap set, not only the fact that the cap set exists and what the numerical values are. So when we initially obtained this result, we were quite excited because we think that it's significant maybe from 2 perspectives. First, as far as we know, this was the first time that large language models were used to discover new scientific knowledge, meaning that this is a probably new piece of knowledge which hadn't appeared in the literature before. The knowledge is verifiably true, and it's about a relevant scientific problem that had been established in the literature beforehand. But perhaps even more interestingly, I think, this also provides a potential new paradigm for using computation for scientific discovery, at least in the mathematical sciences, because here we are using computation not only to discover facts or the solutions directly, but we kind of search for understanding, or we can derive understanding by looking at the functions that construct the solution. So we look for the construction of how to build the solution rather than the solution itself. So throughout this project, we collaborated with Jordan Ellenberg, and we're very happy to hear from him that when he was looking at these functions produced by FunSearch, he felt like he's actually learning something. And I'm not a mathematician, but I can also corroborate this statement that it has been always a lot of fun looking at these functions, trying to understand what they are doing and how they are building these big cap sets. So here on these slides, I was showing the kind of the first function we discovered that builds this cap set of size 512, which was the first new cap set we found. But over time, we ran a few more experiments, and we were actually able to find an even shorter function that builds this cap set of size 512. And it's relatively short, and if you start looking at the conditions that it includes, you can start getting the understanding of, okay, what kind of tricks can you play to generate vectors of length 8 such that no 3 of them are going to lie on the same line. So it's kind of a nice mathematical puzzle. But I still kind of admittedly have to say that at this point, understanding is a bit intangible. Like, what does it mean that we get some understanding or derive some understanding? So after we made this discovery, we were thinking, can we make this a bit more concrete? Can we show that this understanding that you derive from looking at these functions is actually useful for something? Like, you can use it downstream. And indeed, this has been possible. And this actually happened on a slightly like a related problem to CAPSET called the admissible set problem. So that's an auxiliary problem that one can use in order to build these asymptotically large CAPSETs. So it's a very similar mathematical problem. You need to build a large set of vectors that satisfies some condition. And this framework has been used to construct the best lower bounds on this asymptotic rate of growth of CAPSETs as dimension goes to infinity. In this context, this rate is called the capacity of the CAPSET problem. And on the right hand side in the slide, I'm kind of showing the leaderboard of progress on this problem, starting with the work of Calderbank and Fishburne in 1994. And then the gradual improvements by Adele and fairly recently by Tyrell. And so we applied FunSearch in the same way we applied it to the CAPSET problem, to this like related problem of admissible sets. And we were again able to find a function that is able to construct bigger admissible sets than what was known before. And this straight away improved the state-of-the-art lower bound on this problem by a tiny amount. But what was maybe more interesting is that we looked at this piece of code that FunSearch discovered, and it was quite apparent that there is something interesting going on in this function. So if you squint hard, what this function is doing, it's so as input, it takes vectors of length 12. We are building 12-dimensional admissible sets. And the function needs to produce a priority value for each vector, which indicates how likely it is to be included in the admissible set. And so the way this function operates is it loops through all the 12 dimensions in any given vector. And then there is a bunch of if statements. And when any of the if statements is true, then the score is modified in some way. But what's interesting is that when you look at any particular if statement, it will be looking into the vector at various positions, at 1, 2, or 3. And if there are multiple positions being looked at, it's always positions that are 4 positions apart. So it can be I minus 4, I minus 8. And also, whenever this function actually uses the loop index I, it never uses the value directly. It only uses the value I modulo 4. And so when you think about what this function is doing, you actually realize that it's partitioning the 12 dimensions into 4 disjoint groups of size 3, which are within one group, the elements are 4 apart. And if you think about how this function operates, you would realize that whenever you have a vector, and this function is assigning some priority to it, then if in this vector you were to cyclically permute the 3 elements in one of the 4 groups, then the priority would not change because you're always looking at position I minus 4, I minus 8, and only accessing the index modulo 4. And so what this this shows that whenever you have a vector and you do these cyclic permutations, the priority is not changing. So this directly suggests the idea that maybe we should be looking for admissible sets that have this property by design. That if there is a particular vector included in an admissible set, then all the cyclic shifts, or by cyclic shifts I mean these cyclic permutations within these 4 groups of 3 dimensions, are performed, then the resulting vector will also be part of the admissible set. So in a way, this admissible set would have this symmetry or closure property. So this is a hypothesis. Like there is no a priori mathematical reason I know of why admissible sets should possess this property. So it is kind of a restrictive assumption. But if we encode this assumption in the problem statement, this results in a problem that's more restrictive. So we can now only find symmetric admissible sets. But the problem is a much, much smaller search space. And so by doing this, it actually turned out that we can indeed construct much bigger admissible sets than what we were able to do before, thanks to this additional constraint. And in fact, the improvement in capacity that we obtained this way is much bigger than the initial improvement we got just by applying FunSearch to the problem out of the box. So here I hope I kind of demonstrated that there is at least this one case where the understanding you get by inspecting the function discovered by FunSearch can lead to a very concrete and tangible next step that helps you improve results even further. So just as a very quick overview of how FunSearch operates, you start with a specification which contains this evaluate function I talked about before. And you also have a database of programs that has the solutions discovered so far. You initialize this with an initial solution. And then what happens throughout the FunSearch loop is that you sample some programs from your database. You use them to build this prompt for the LLM that I showed before. And then you show it to the LLM. And the LLM will give you some candidates for how to improve the function in the prompt further. It can give you multiple candidates. Because these are in the form of source code, you can automatically evaluate them, check them for correctness, check how good they are, and then the best ones you can put back into the database. And this way you close this self-improvement loop that you can run for as long as you like, and at any moment you can extract the best program found so far. So now shifting gears a little bit, after the success with Capset, we are also curious whether we can apply this framework to discovering practical algorithms. So we looked at the problem of online bin packing, where you have a stream of items coming in of various sizes. You need to pack them into bins. And of course, you want to minimize the number of bins you use up to minimize costs. So this comes up in shipping or in scheduling jobs in data centers. And again, out of the box, with FunSearch, we have been able to find a heuristic function shown on the right that generally uses fewer bins than established heuristics. Now, in the animation, there is like an anecdotal case where FunSearch uses 5 bins instead of 6 that is needed by the kind of usual heuristic. But of course, we also checked on an established benchmark that this is quantitatively true on average. So towards closing, let me just reflect on what kind of problems we think FunSearch is a good fit for. First of all, as I mentioned, you need to have an efficient evaluator. So given a candidate solution, you need to be able to tell in our implementation within 20 minutes how good that solution is. Ideally, you will also have a smooth scoring feedback. So your problems shouldn't be binary, like solved, not solved, but you can iteratively make an improvement. Like with the capset, you can gradually find bigger and bigger capsets. And then finally, if you have some prior knowledge about the problem, you can encode it in the prompt and thereby inform the language model about what kind of modifications might make more sense. Okay, so let me skip these few slides. I also want to briefly mention the limitations. I have to say experiments are relatively expensive. So to obtain the best CAPSET results, we did need on the order of 1 million samples from the large language model. Now this cost is, I'm happy to say, plummeting over the past few months, but it is still significant. We are for now constrained to generating fairly short Python functions, so on the order of maybe tens of lines of code. I mentioned we need fast evaluation, and we also have this kind of maybe strange feature for now that we do not benefit from using better language models necessarily. Like it's not worth using a large language model, a bigger language model, to justify the increased cost, indicating that for now we are not fully utilizing their reasoning capabilities. Okay, so in summary, I talked about FunSearch. This can be viewed in different ways. One is that it's a framework for searching in solution space, or sorry, in function space, so searching for functions that construct solutions rather than searching for the solutions themselves. You could alternatively just view it as powerful code evolution, maybe as genetic programming with a much more powerful mutation operator provided by the LLM. Maybe a third view on FunSearch is that this shows the way how you can utilize language models already today to discover new knowledge in the mathematical sciences. And finally, and more generally, thinking beyond science, this is a technique that is able to kind of augment the intelligence of a pre-trained language model by spending more compute at inference time, querying the model multiple times in a smart way. You are able to get results that go far beyond what you are able to do just by asking the language model once. With that, thank you for your attention, and I'm happy to take any questions.